Hi guys, today I want to introduce you guys about this topic. It's basically about a Jacob Benson Katsuki Execute Station, and it will be done by me, Ni, and Rolf. And you will have an idea about how the structure change of the catalyst can actually lead to change in the catalytic work, and what we can deduce on the role of 5-phase in determining selective discrimination, and also how the ligand substitutes on the manganese catalyst influence the reaction energy. So let's start it. Uh, for example, just like the PPT shows here, it's a two-step Jacob-Benson Katsuki X-ray station, and it's a type of oxygen transfer reaction. And what we gonna study is here there's an intermediate shows here. It's called the Jacob-Benson catalyst, which is produced in the first step and can be used as a carrier in the second step. There has been a lot of papers talks about this kind of oxidations, reaction profiles, spinning states, and also other things, but the catalyst turning has not been addressed yet. So this paper is designed to talk about this kind of aspects, and we will introduce this paper following the sequence listed here.
Now, in regards to computational details, the density functional calculations on various manganese systems, which are the active catalysts in the epoxidation of olefins, these were calculated and these were corrected for exchange and correlation according to Beck and Perdue, the Beck and Perdue functional, aka BP86. This was thought to be a suitable and appropriate functional for the systems that we were testing. Manganese, the local minima geometry was optimized within the RJ approximation using the turbomole system, and the transition state were optimized and characterized within one imaginary frequency using the Gaussian system. The manganese has been described on a polarized split valence basis, and the manganese was treated with a valence triple X is the Greek pronunciation with a valence triple X basis plus one additional P function. These are the references for the turbomole system used for the local function correlation, and the Gaussian system used for the correctional functional. In regards to the electronic structure of the manganese system, salin and acinan, the most stable geometry of acinan is the square planar coordination. It's an electronic quintet where the less stable triplet state is 30 to 40 kilojoules per mole high in energy. The singlet state is not considered to be catalytically significant, as the singlet state undergoes a distortion of the square planar coordination. Now, in regards to the tables I'll show you in the next slides, 5Mn3 refers to the quintet state geometry of salin and acinan, and singlet and triplet both have an oxidation number of +5. Here we have the two tables of the relative energies of the quintet and triplet geometries of acinan and salin. As we can see from table 1, complex 2 shows the largest quintet triplet splitting, and complexes 2a to 2f are energetically more favorable in the quintet state than they are in the triplet state. This is due to electronic withdrawing ligands in the 5-5 position, such as nitrogen dioxide, which raise the quintet triplet gap, and alternatively, electron donating ligands within the same position, such as a methyl ester, which lower the quintet triplet gap. In table 2, we can see that in accordance to previous studies, complex 3 actually prefers the singlet state compared to the triplet state, with the triplet state being 5 kilojoules per mole high in energy, showing it's less stable. This is different to complexes 3A to 3F, where the triplet state are more energetically favorable than the singlet state. This is due to the extended aromatic system, which permits effective electronic destabilization. This destabilization stabilizes the singlet state to the triplet state, with the singlet state being approximately 3 kilojoules per mole high in energy. Therefore, the triplet state is much more energetically favorable than the singlet state.
Hi. So now we are entering the electronic property part. So in this part, they are using the computational method and trying to establish sensible molecular descriptors to be able to develop a better understanding of this three question list here. And from that, they will have an idea like how does the substitution actually influence the catalyst. That's like we talked before, and we use this method we call QSPR to establish the molecular descriptor. The reason that why it can determine that such a relationship is because this method uses a lot of empirical parameters related to the molecular and electronic molecular properties, and the most used is Hammond's constant. So you can see here in the QSPR studies, and it's talk about the electronic resonance and its conjugate effect. And it used two experiments to discuss the previous three questions. And the first experiment, which you can see here, and the conclusion and the relationship we found here actually consistent with the other oxygen transfer reaction, which is medicated by the other similar low valent transition metal complexes. And the charge and the orbital analysis performed about the transition state of the ethylene oxidation actually suggests that this kind of oxidation reaction is can be recognized as the electronic attack of oxygen as the olefinic double bond, and it's expected that a smaller amount of charge as the oxygen the move forward the electrophilic attack as a homo olefinic system. Therefore, the system with a smaller amount of negative charge as the oxidation center should be resolved earlier and more ethylene transition state, and vice versa. And the second experiment, just like the previous one, is just need a further interpretation to get the bond strength value from this equation. And so we can get the relationship shows here in the diagram. And from the results, we can see the bond strength difference caused by the electron donating and the electron withdrawing group. And the first conclusion, just like the last experiment, the weaker bond strengths are actually caused earlier and more ethel-like transition state. And with combination of these two experiments that we discussed previously, and then the overall conclusion can be get here, and we can get this kind of relationship diagram.
So in these slides, I will talk about the correlation of transition state geometries with Hammett parameters. In the paper, they also optimized the transition state geometries for the first CO bond in formation 4A to F, which are shown in the figure below here, if you can see it. And the epoxide formation is expected to proceed through first and second transition states, which correspond to the formation of the first and second CO bond. However, the first transition state in which the enantiomer selectivity is determined, since it is the first transition state leading to the formation of the first chiral carbon atom, and the second transition state could be determining for the overall reaction rate, for the distribution ratio of cis or trans products. The graph here shows the correlation between the modified Hammett constants and the bond length of CO bond. Distances for the evolving CO bond range from 1.98 to 2.05 angstroms, and systems with electron withdrawing groups react in an earlier, more EDUC-like transition state, whereas a system with electron donating groups react in a later, more product-like transition state. Systems with electron withdrawing groups also show a longer CO separation than that with electron donating groups. There are some further considerations based on studies about the enantiomer selectivity of epoxidation. First, a late transition state requires a certain proximity between the olefin and the manganese oxo complex, leading to less amount of spatial separation between substrate and catalyst, and enhanced differentiation of diastereomeric transition structures. In addition, enantiomer selectivity is governed by interactions of the saline ligand, which in the transition state geometry adapts a folded geometry forming a chiral pocket and the incoming olefin. It is also suggested that because of the electronic influence of the 5,5 substituents, systems with a stronger MNO bond require a larger amount of activation energy and therefore react in a relatively late transition state. To conclude, electron withdrawing substituents and possessing weak MN bonds should react in an earlier, more Etoch-like transition state, vice versa. Besides, enantiomer selectivity is tied to the position of a transition state along the reaction coordinate is supported in the current work. Finally, electronic effects exhibited by the 5,5 substituents of the catalyst manifest themselves in a turning of the MN bond strength. That's the end of our presentation. Thank you so much.